Can you view my screen?
Yes, sir.
All right. Okay. So let me now start proper integral. So right. So look at the following graph. Just look at the following graph. So though that part is not good, let me. All right. So the function, this function is y equal to 1 over x square. So this is the point 1. Now suppose you want to find this area. You want to find this area. So how do you find this? Right? So this is the question. So this side it is going towards infinity and we start from 1. So so we want to find the area under the curve y equal to x square, 1 over x square, and on, let's say, 1 to infinity, right? So what do you want to do is you want to integrate 0 to infinity 1 over x square dx, right? But we have defined a Riemann integral for bounded interval AB, right? We have not defined the the integral for infinite one. So you should define this. So this is what we want to find, right? The definition. So you need first a definition of what to. Of course, it is natural that you have to go with limit. So let me come back here. Before that, let me define this the integral. If is Riemann integral on, let's say, A to C for all C less than B, then we define integration A to B fx dx. So B can be infinity, right? So B here B can be infinity. So how should I write? So A to infinity closed. Let's do this. Then we define this one as limit C tends to be integration A to C fx dx. Right? Is this clear? Provided the limit exists. And limit exists means it has to be finite. So maybe I should write it also exists and finite. Sometimes limit can be infinite. Yeah, so is this definition clear? So in our case here, we would like to, so for example, integration A to infinity fx dx is by definition limit n tends to infinity, write small n here, integration A to n fx dx. All right. So provided, of course, provided the limit exists and finite. Right. So now let us come back here. So integration 0 to infinity dx by x square is, of course, we want this one limit n tends to infinity, integration 0 to n dx by x square.
Sir,
Yes,
sir, our main aim was to calculate the area from 1 to infinity, right? That's what
right.
we.
Right. So instead of 0, yeah, 0 is another problem. We'll come to it. So put 1 here. If you don't put 1, then there'll be problem at 0 also. So we'll explain that part also. So at one time you consider 1 point, so there is a problem. Here infinity is the problem. So here now uh, this is perfectly fine, right? So this one, so this one, uh, this is perfectly fine. This is fine because the function 1 over x squared is continuous on 1 to n and hence Riemann integral. All right. So let us evaluate that. So integration 1 to n dx by x squared by using fundamental theorem of calculus. So we get minus 1 over x square, and the limit is from 1 to n, so which is minus 1 over x, right? So 1 of minus 1 over n plus 1. So now you take limit, n tends to infinity, 1 to n dx by x square is limit n tends to infinity, minus 1 over n plus 1. So this 1 over n goes to 0. So this becomes 1, right? So this area becomes 1. All right. So let's continue the definition here a little more. So definition, if what is this? So this one limit a to c, limit c tends to b, fx dx exists, then we say that the integral integration a to b fx dx is convergent. If limit c tends to b integration a to c mod fx dx is exists, then we say integration a to b fx dx is absolutely convergent. Convergent. All right. So b could be infinity. So you can, if you are confused with b, you can take b to be infinity for simplicity. So take b to be infinity for simplicity. All right. Now consider another example. We look at fx equal to 1 over x on 1 to infinity. Okay. And what about, does integration 1 to infinity fx dx convergent, or is convergent? What about absolute? Okay. So if you consider 1 to n fx dx for the time being, which will be integration 1 to n dx by x, right? Now this one, you know, it has antiderivative here, right? 1 to n. So this is log of the natural logarithm, log x. This is 1 to n. So which is log n minus log 1, which is 0. 0. As so limit n tends to infinity, integration 1 to n fx dx is equal to limit n tends to infinity log n, right? So what is it? Yeah, infinity, right? So yeah,
Yeah.
right. It doesn't go very fast to infinity, but it is going to infinity as n tends to infinity. So this is infinity. Hence 1 to infinity dx by x is not convergent. So which one can say divergent. All right. So hence it is not absolutely convergent either because when mod x is equal to x here in this range, right? So look at the graph of 1 over x, right? Look at the graph of 1 over x. This this doesn't go very near to zero here. So I'm considering and then one is something like here, right? So this part it goes to zero again. But you see, compare with the graph here in the beginning. Here it converges and in this area small, right? And in this case, the area is infinite. V under the curve is infinite, right? Okay, look at another example. So example 3, integration 0 to 1 fx dx, where fx is 1 over x to the power alpha. Alpha is bigger than 0, right? So what is the problem? Problematic point?
That's it. At zero, it's going to.
Right. At 0, it is going to blow up, right? So in this kind of integral, so here we have defined for upper limit, right? Similarly, one can do it for lower limit as well. Okay. So we consider here, consider the following. Consider Yeah, I'm sorry, the internet was kind of gone for a few minutes. So it's irritating. Still, let's start. Yeah, can you hear me now properly?
Yes, sir.
Oh. Yeah, so we use fundamental things. So this part you have heard about, right? I didn't know where when the connection uh, went away.
Sir, you are not presenting.
I'm not okay. Okay, so I need to present, right? Yeah. Hmm. Yeah. Now is it fine?
Yes, sir.
All right. So so did you see this part? 0 to 1 integration fx dx, where fx is equal to 1 over x to the power alpha. Yeah.
So the screen paused after the starting of this question.
Now it's paused, or you can see.
Now I can see.
Okay. Okay. So this fx equal to 1 over x to the power alpha. Now the problematic point is 0, right? So we consider an epsilon between 0 and 1, and let's look at the integration epsilon to 1, right? So this one. Now since 1 over x to the power alpha is Riemann integrable on this interval epsilon to 1, we use fundamental theorem of calculus to evaluate it, right? So what would be it? Minus alpha plus 1 by minus alpha plus 1, and then the limit epsilon to 1, which is 1 by 1 minus alpha minus epsilon to the power 1 minus alpha by 1 minus alpha. All right. Now we look at limit epsilon tends to 0, integration epsilon to 1 fx dx is equal to limit epsilon tends to 0 uh, 1 by 1 minus alpha minus epsilon to the power 1 minus alpha by 1 minus alpha, right? So this is equal to what? This is equal to 1 by 1 minus alpha if alpha is less than 1, and this is infinite if alpha is bigger than 1, right? Is it fine? For alpha equal to 1, the case we already dealt. So in this case, you see here integration 0 to, so this one would be uh, definition of this 0 to 1 fx dx, which is by definition limit epsilon tends to 0, epsilon to 1 fx dx, which is equal to 1 by 1 minus alpha if alpha is less than 1. And the integration 0 to 1 fx dx diverges if alpha is bigger than 1. Is it fine? Yeah. So we can actually look at the problematic problem at the lower limit as well, and we can evaluate. So this is going to be important because this kind of integral, whether this integral exists or not, or integral is bounded. So this will be playing an important role later on. Okay. Is this fine? So these points, problematic points, are called point of singularity. So an exercise. Determine when integration 1 to infinity dx by x to the power alpha is convergent. Right? Any question here till now? Is it clear? Everything?
Yes, sir.
All right. So let's look at when such this integral exists. So the test of convergence. So one is the theorem. Select f be a Riemann integral function on a to t for every t greater than equal to a. Assume that there is a positive constant m such that integration a to t mod fx dx is less or equal to m for every t greater or equal to a. Then both a to infinity fx dx and a to infinity mod fx dx exist. So which means this is absolutely convergence also. All right. So what a condition you need? You need this is bounded for every t, right? For every t greater or equal to. Right. So this things might look complicated, but we are what we are assuming is this should be true for every t greater or equal to. So that actually is quite strong. So proof, define capital Ft to be integration a to t mod fx dx. So clearly f is an increasing function. You look integration of a positive function and you are integrating the function is depending on the range upper limit, so it is increasing function. And by assumption, mod of ft is less or equal to m for all t bigger equal to a. So this implies this limit t tends to infinity ft exists, right? So it is increasing and bounded. Therefore, integration a to infinity mod fx dx exists. And if f is absolutely convergent, integration f mod f is integration f is absolutely convergent, then integration f is convergent. That is a simple proof. Let's look at this one. Fx minus fx, which is also less or equal to 2 mod fx, right? Now look at limit t tends to infinity, integration a to t mod fx minus fx dx is less or equal to limit t tends to infinity, 2 will come out, integration a to t mod fx dx. Right, so this side get equal to 0. So therefore, this implies the first integral will exist, this integral exists. So this implies integration limit t tends to infinity, integration. So this one exists. Fx dx exists. Now you just do these things. Integration a to t. So the which is nothing but integration a to infinity mod fx minus fx dx. Now you do integration a to infinity 2 mod fx dx minus infinity x dx, right? So which is nothing, not 2 mod x, just this. So which is this is also exist. It's convergent, which is because both are convergent. So this is nothing but integration infinity a to infinity fx dx. All right. So it is simple to see that if f is integration f is absolutely convergent, implies it is integration f is convergent. But of course, not the converse is not true. We'll see an example. Yeah, before going further, yeah. So the following, let me put the following as an exercise, which is there in the notes, but it is not very complicated. So I put it as an exercise. Suppose f is continuous monotonically decreasing function on infinity, assume f is greater or equal to 0, non-negative. Then the integral integration a to 0 to infinity. Did I put 0? Yes. No problem. It is one can take a to infinity. 0 to infinity fx dx converges if and only if summation fn n from 0 to infinity is converges. So the integral converges if and only if the series converges. Does it surprise you? Yeah, so let me give a hint. The hint is so that f of n plus 1 is less or equal to integration n to n plus 1 fx dx less or equal to fn, right? And then take summation. And I'll yeah. So now several of the properties of integration, Riemann integration, you can take to improper integral also. All right. So for example, integration by parts. Yeah. So before uh, going into even further to integration by parts, let me put case 2. Let f and g be positive and limit x tends to infinity fx by gx is equal to some constant a greater than 0, then integration a to infinity fx dx. So this is of course we Riemann integrable on a to n for every n. Converges if and only if integration a to infinity f g x dx converges. Okay. So we are considering here the limit. So the function will be Riemann integrable on any bounded interval, positive and Riemann integrable on uh, a to n for all n natural number. So this. So we are not going to go to proof, but this will be useful. You can try to show the proof because I mean it, at the infinity f and g will have same growth. That is it. That is what this limit means. Okay. So now let's look at the integration by parts. So again, assume f is continuously differentiable on a to infinity and g prime x equal to gx. Of course, g, f and g are Riemann integrable on a to n for all n in n. We need this one. And of course, this improper part we look at later. Then what I'm just giving a proof, not just how to get to the statement. I'm not writing statement and then proof. So now if you look at this integration a to n fx gx dx, right? Then by integration by parts, you can actually have fn is capital Gn. So by integration by parts minus fa ga minus integration a to n f prime x gx dx. All right. Now we need the limit exist, right? So if this here here it is a condition. So let me write. Then I'll just limit n tends to infinity. Fn gn exist. Right. So this is a condition. This is a condition or an assumption. Like then if this is b, then you have a to infinity fx gx is equal to b minus fa ga minus integration a to infinity f prime x gx dx. So this is a condition. Another condition is this limit exists. Well, you see, once this limit exists, then this integration is finite or exists if and only if this integration exists. This convergent. This is convergent. So the point is here that sorry, did I write? No, this is wrong. Gx dx. Fine now? Is it fine now? All right. So let's. So we have this one. Once this is a condition, another condition we would require is well, this is definitely true, and this one is nothing but limit of n tends to infinity integration a to n f prime x gx. All right, and this is as it is. So this is limit n tends to infinity integration a to n fx gx dx. All right. Now this is here is test. Did I write test 2? Yes, test 3. Suppose G is bounded. G is bounded. That is, suppose G is bounded So this is 1, 2, that is, there exists m greater than 0 such that mod gx is less or equal to m. Second thing is fx tends to 0 as x tends to infinity. Third thing is integration 0 to infinity mod f prime x dx is less than infinity. This f prime integrable is integration 0 to infinity f prime is absolutely convergent. Then integration a to infinity f prime x gx dx exists. All right. So which means this part exists. That means this part will also exist. Right? This part exists. We gave a test where this exists. This exists. Now that will give you this part exists. All right. So you see G is bounded. So you take modulus less or equal to m here. And this f prime dx that goes to 0 as this is less than infinity. Well, absolutely. That would give you, it's natural, this condition gives you the existence of this one. All right, let's look at an example using these things. Example 4. I'm not going to give a proof here. Well, proof is easy coming from here. I mean, going from these things, all this together, you try to, I mean, those interested can try to prove this one. And this one gives you existence of this, and hence you have existence of this one, integration fx gx dx at a to infinity. Now, this one, I wanted to give this example, sine x by x dx. All right. So here you see as x tends to 0, sine x by x is 1, right? You know already. So at x equal to 0 is a removable singularity for the function sine x by x. So that means if you define fx to be sine x by x when x not equal to 0 and 1 when x equal to 0, then f is continuous. All right, is this clear? So once this is continuous, you see integration 0 to infinity sine x by x. You can look at this one as sum of two integral with the sine x by x dx plus integration 1 to infinity sine x by x dx. So this part is fine. So this part is fine. I'm not going to evaluate, but I'm seeing that showing that this converges. So look at this one, sine x by x dx, right? And here we will use this one. We'll use this test 3, right? So which means look at fx. So we need what? Fx goes to 0. So consider fx to be 1 over x, 1 over x, sorry, and gx is equal to sine x right? So mod gx is bounded by 1. Fx tends to 0 as x tends to infinity. F prime x is 1 over minus 1 over x square. So we know integration f prime x 1 to infinity dx is integration 1 to infinity dx by x square, which is 1. We already know it, right? Oh, sorry, this is test is it's just not f prime. Did I write? Yeah, f prime. That is fine. No, I think something is wrong. Yes, something is wrong here. So f prime gx. Mm, so we need to consider this one, this integration by parts formula here, and here, of course, this should be exist. This should exist. Oh, g I need to change a little bit. So g will be g prime is g prime has to be this g. So g prime has to be this g. So this small g is um, yeah. So here small g is this one, and capital G is what is capital GX? Minus cos x, right? G prime is G. Capital G prime is small g. Yeah. Okay. So now this one, this implies integration by test 3, integration 1 to infinity, this one f prime x gx, f prime x gx, capital gx exists by 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 integration by parts using integration by parts. We have integration fx gx, fx gx dx 1 to infinity, which is nothing but which is integration 1 to infinity sin x by x dx. All right. So this one will be, so this part, you see, this part vanish, right? This part would be, so what is this part? So 1 to infinity, this is 1, and g1, so some constant. So this exists. So remark, integration 0 to infinity sin x by x dx is convergent, but not absolutely convergent. Convergent. Okay. Next time we'll show this part and we'll define beta and gamma functions. All right. Any question here? Yeah. Is this clear? Here I got confused a little bit. Yeah.
Yes, sir. Now it is fine.
Okay. Okay. So next time we'll see this absolutely not absolutely convergent. That is also for that we need a kind of test, and we'll do that, and then beta gamma function will define.
Sir,
Yes.
sir, I have doubt from last class.
Yep.
In integration 8 class, you gave us an exercise of to prove the theorem of change of variables.
Yeah.
I applied upper and I calculated upper and lower sum of the f of x, f, and then converted x into phi of y. Then I applied mean value theorem.
Hmm.
I am stuck there after the mean value theorem step.
Okay, so let me go where I gave it. So it is in the notes, is it? Or
Yeah,
in
it is in notes, but it was given as an exercise. Not its proof was not given. Its proof was an exercise.
okay, so proof was an exercise. So let me see the notes first. Integration 8 you made, right?
Yes, sir. Integration 8.
Yeah.
Page number 2. Yes, here.
This one, right?
Yes, sir.
Okay, so what was the problem?
Um, I first suppose I taken some partition of AB from
Hmm.
x0 to xn. Then I took partition of CD such that partition of CD y0 to yn such that yi
Mhm.
is equal xi is equal to phi of yi
Right,
for all I 0 to n.
right.
Then I calculated upper sum and lower sum. I used that formula for upper sum and lower sum,
Hmm.
and then I subtracted lower sum from upper sum, and made an equality such that the upper sum is minus lower sum is smaller than epsilon.
So integration a to b fx dx, did you calculate this one in terms of integration c to d? So
Yes, sir. I put
yeah,
phi of I put x instead of xi I put phi of yi.
right. Phi of yi and what about xi minus 1?
Yeah, I put phi I of y minus one, phi of y minus one, comma
Uh-huh.
phi of yi. But then
Right.
I converted f of phi yi and put yi minus one to yi. That
No, there will
interval
be
for
there will be
supreme
this phi
human.
prime, right?
Yes,
Here
sir.
you have to use mean value formula, mean value theorem.
Yes, sir. I applied mean value theorem, but I am getting some ti in between phi I minus one to yi minus one to yi.
Right. You will get that. Yes. So you'll get that. So that part is you are getting some ti, right? So if you look at
Yes, sir.
upper sum and lower sum, you get this one. That is fine. So what you want to do is, instead of that one, you look at Riemann sum, right?
Yes, I will
So
have to calculate summary. I will have to prove that the upper sum of in right hand side of this equation.
yeah,
I will have to get the some form like which would look like upper sum and minus lower sum of f of phi y phi dash
right,
y.
right. F compose phi prime y. So right. So this one actually, the point is here. Uh, right. So you are right saying that there is another pi is coming into the picture, right?
Yes, sir. I
Another
am
pi.
able to prove that the lower sum would be smaller than lower sum. Yes. If I can easily convert from phi dash of ti to infimum of phi dash y of
Mhm.
interval phi I minus 1 comma yi.
So did you use this Riemann sum argument?
Which one?
Riemann sum, instead of this lower sum and upper sum, we had proved that equivalent, it is equivalent to show that any ti you take in between xi minus 1 xi, and this the right left hand side integration a to b fx dx is equal to the limit or whatever, the sum of integration f of ti
Then I will have to
xi
prove
minus
this.
1 xi minus 1.
But then I will have to prove that it would work for all ti's, which will come between yi minus 1 to yi.
Yeah, it is actually in the theorem. It is true that it works for every ti.
It was for.
It works for every ti inside there. In the theorem, it is already proved that it works for every ti inside xi minus 1 to xi. So therefore, you can actually change this one. So you look at Riemann sum instead of lower and upper sum. And there also you need to, so f of pi will be, f of pi will be there, and there will be this xi minus 1, where you have p of yi
So I
minus
will
p
take.
of yi minus 1, and then p prime of whatever this one si, let's say. So you get, you first, whatever first thing is to do is mean, you do the mean value theorem for pi, okay, on this partition xi minus yi yi minus 1 yi, okay.
Yes,
Then
sir.
on this, so you get some points inside, right? You get some points inside that xi minus 1 to, sorry, yi minus 1 to yi. You'll get some points, right? Let's call it si, right? And
Sir,
then
I'm
you
not
look at,
getting it after TI. I got the by MVT by mean value theorem. I got TI. Then what will I do?
yeah, so let me show you here. So the point is, you have to look at, you have integration a to b fx dx, right? And you have phi from cd, sorry, cd to ab, all right? And
Yes, sir.
here, so you look at partition of AB, uh, AB, and partition of CD correspondingly. So here partitions are xi plus 1, so on, and partition of CD correspondingly, because phi is on to everything. So yi minus yi plus 1, so on, right? Now on this yi on yi yi minus 1 to yi, apply mean value theorem on phi, okay. So that means phi
Yes,
of yi minus phi of yi minus 1 is equal to, so there exists, let's say si belongs to yi minus 1 to yi. So this is phi prime si into yi minus
yi minus 1.
yi minus 1. All right. Now
Yes.
you look at this Riemann sum for this integration. For integration Riemann sum. So you look at the points here. You look at ti, which is tj, which is, let's look at ti, which is phi of si. All right. So ti you look at phi of si, and this will be inside xi minus 1 to xi. So this, you look at this sum ti xi minus 1, and then sum over I, over whatever partition you take. As I tends to, this n tends to infinity, I equal to 1 to n you take, and n tends to infinity, you get the limit because f is integrable given to you, right? So now this one, I equal to 1 to n, you get f of phi of si. And here this you get phi of yi minus phi of yi minus 1, right?
Then we will apply
You
mean
get,
value theorem.
you already applied, and that's correspondingly
Yes.
that si you get ti. Other before, I mean, you have to apply mean value theorem before.
Okay.
You see this? The problem of this taking different one si and different ti was coming because you applied mean value theorem inside the sum. You have to do it earlier.
Okay.
Compose P si, and then here this P prime si. Now see, these points are same. These points are same because
Yes,
we
sir.
have already done in this way. yi minus yi minus, and this is the Riemann sum. Riemann sum for what? For this integration a c to d, f compose phi y, phi prime y dy, right?
Yes, sir.
Yeah. So this is how you make it precise, write it properly, but this is the idea.
Sir, but where we used upper sum and lower sum here?
Yeah, if you do upper sum and lower sum, then you have to go through this the proof of this one. The Riemann sum is equivalent to looking at upper sum and lower sum. You have to do this epsilon delta argument, all this, right? Because I mean, we proved that theorem is equivalent, showing upper sum is equal to lower sum, upper integral equal to lower integral is equivalent to show that this n tends to infinity, this limit exists. Is that equivalence needed some work, right? So if you don't want to do, you go with that one, then you have to go through that the argument in that theorem. So you can try experimenting. That way you will
So
understand.
this argument is enough, and I don't need to take upper sum and lower sum here in this proof.
Yeah, in this case, yeah. So there are equivalent criteria of Riemann integration, right?
Yes, sir.
There were some equivalent criteria. So this was equivalent to showing that lower sum upper sum is less than epsilon. That one we have shown.
Okay, sir.
Okay. Any other question?
No, sir.
All right.